This one should be easy for you to spot as well. It's similar to single replacement reactions. The big difference is that we are exchanging ions between two compounds this time instead of just one. And at the end of a double replacement reaction, we end up producing either a precipitate, a gas, or water. So if we look at our example, we have AX plus BY. Remember, Y is something new, yields AY plus BX. So it's kind of like square dancing, if you've ever heard of like do-si-doing or something like that. You switch partners. So A starts out with X, but at the end of the equation, A switches partners, ends up with Y on the product side. Same with B. B starts with Y, at the end ends up with X. So if we take a look here, we end up with the same idea. So we have AX, here's our A, here's our X. Chlorine is not going to end up with bismuth at the end of the equation. Chlorine is actually going to switch and bond with hydrogen, which is our B. Sulfur is our Y, so sulfur is going to end up with bismuth at the end of the equation. Moving on, last one and possibly your favorite is the combustion reactions. This occurs when a substance reacts with oxygen, releasing energy in the form of heat and light. So fireworks, campfires, things like that, heat and light are some of the products that we end up with. That's why when we have fire drills, teachers are advised to close windows because when you close windows, the oxygen cannot get into the room. If you had the windows open, the oxygen would actually let the fire grow more. So if we look at this example, P4 plus O2 yields P4O10. Oxygen is the key thing here. You might have already noticed this is a synthesis reaction. Here's our A plus B yields AB. However, the distinguishing characteristic of combustion reactions is that you are reacting with oxygen every time.
All right, now we're going to continue on to talk about chemical energy. This is one of the words that you should have looked up at the beginning of the chapter when we paused. Chemical energy is stored in chemical bonds. Those bonds that we talked about between Cl2, when we have our subscript 2, it's two Cl's bonded together. That line right there represents the bond that they have between the two atoms. Chemical energy is stored in these bonds. Okay, so how to get chemical energy? One way is to break the bonds of the reactants. Remember, reactants are found on the left side of the chemical equation. That's how we get energy. We can break the bonds. If we form bonds between products, we are storing that energy. Remember that the products are found on the right side of the chemical equation. So we are either breaking the bonds of the reactants to release energy, or we're forming bonds of the products to absorb energy. So chemical energy is either released or absorbed, just like I said before. When it's released, it creates a reaction called exothermic. Exo means out or exiting. So exo, out. So it's releasing the energy. The energy is going out of the reaction. In endothermic reactions, endo means in, the energy is being absorbed by the chemicals in the reaction. So endo means in, absorb, they're taking the energy in. Those are the two types of reactions that we're going to talk about in this chapter. Let's talk about them a little more in depth. For exo, we're going to remember that exo means out. Write that up there again for you. Exothermic reaction. The energy is being removed, being released. Okay, so we start on the left side of our equation. We start with our reactants. In our graph here, we have amount of energy on the left and progress of the reaction on the bottom, which means time. Progress of reaction is just time. Okay, so we start with our reactants. As the course of the reaction goes on, we decrease the energy because the energy is being released. Okay, so this is the energy coming out from the chemical reaction. And then we have our products here at the far right. Okay, so what's going on in this equation? When there's an exothermic equation, we release energy out of our reactants, and then we end up with our products. So the energy of the reactants starts out much higher than what we end up with in the energy of the products. It's much lower. So one of the defining characteristics of an exothermic reaction is that the energy of the reactants is greater than, that's what that arrow right there means, greater than the energy of the products. So it's important to remember this graph and also the distinguishing characteristics. What about endothermic reactions? When we have endothermic reactions, again, endo means in, so that means the energy is coming into the reaction. So energy is absorbed as the products are formed. So this graph looks a little different. The reactants start out at a very low energy. As the reaction continues, the energy is being absorbed into the reaction. So here's our energy. And then we have our products at the end after the energy has been absorbed. So the energy of the reactants is here, it's much lower. The energy of the products is up here, it's much higher. Therefore, the energy of the reactants is less than, that's what this caret right here means, the energy of the products. Okay, so these are the defining characteristics of endothermic and exothermic reactions. As you will see, the graphs, whether they are absorbing or releasing energy, and the energy of the reactants or products are opposite for each of these reactions. It's going to be very important when we're going to distinguish between the two. There's the law of conservation of energy. We talked earlier about the law of conservation of mass. The law of conservation of energy says much of the same thing. It says that energy, so we're talking about energy instead of mass now, of the reactants must equal the energy of the products. Now there's a little bit of a discrepancy with what we just said, because one of the defining characteristics that we said of exothermic reactions was that the reactants was greater than the energy of the products. And then the opposite holds true for the endothermic reaction. We said the energy of the reactants is less than the energy of the products. That was one of our defining characteristics. So how can this hold true for these types of reactions, and can we also honor the law of conservation of energy? Well, it's very simple. The answer is heat. Okay? With heat, we are able to maintain the law of conservation of energy and also hold true with our reactants, the energy of the reactants and the energy of the products and their relationship in exo and endothermic reactions. Here's our graphs again. This is an exothermic reaction. Okay? The energy is being released, so it's leaving. The reactants start out higher, and the products end up much lower in their energy. Therefore, we have to add heat at the end of the reaction to make it the right side and the left side equal each other. Since the reactants start out at a higher energy and the products end up at a lower energy, products need a little bit of assistance. And that little bit of assistance comes right here with the energy and the heat that's being released. So we need to add heat to the left or the right side of the equation. Endothermic reactions, this is an endothermic reaction graph, is the exact opposite. We are adding heat, adding energy in. So the reactants start at a much lower energy level and the products finish at a much higher energy level. Therefore, the reactants are less than the products. So in order to get them to equal the energy of the products, we have to add heat. So here is where we add that heat, and we're going to add it to our reactants. Okay? This one, we are going to take our heat and add it to the products. We're going to add heat to whatever ends up with the lower amount of energy. So here it's the products, here it's the reactants. Again, these graphs are very important to distinguish between exo and endothermic. You're going to have to be able to identify which graph is which and then tell us which side the heat belongs on. Okay? So heat is what helps us maintain the law of conservation of energy in exo and endothermic reactions. Okay, so let's do a quick summary. How to determine exo and endothermic reaction. Okay, first we're going to look at the relationships of the reactants and products. When we look at our graphs, we're going to see which reactants has, whether the reactants or the products has lower or higher energy. This is going to tell us whether it's an exo or endothermic reaction. When we look at the graph, we can also see whether heat was released or absorbed. The third way that we can determine whether it's an exo or endothermic reaction is to look at whether heat was added to the products or the reactants to maintain the law of conservation of energy. Okay, so we're going to talk a little bit about reaction rates. Reaction rates tells you how fast the chemical reaction is going. Okay, there are several factors that affect the reaction rate. The first is temperature, the second is surface area, the third is stirring or agitation, fourth is concentration, and the fifth and probably most important one is catalyst. We're going to talk about each of these a little more in depth. So for temperature, generally, and you want to write this down, this relationship, increasing temperature will increase the rate of the reaction. Okay, that's a very important relationship. The reason for this is when you increase the temperature, you also increase the motion of the particles. So we talked a little bit about if you have an ice cube, it is solid water, and in order to turn it into a liquid, you have to increase the temperature. And when you increase the temperature and it becomes a liquid, the particles are moving quicker. If you increase the temperature even more, it becomes a gas and the particles are moving even faster. So the faster the particles are moving, the more likely they are to collide and the more likely they are to react. So make sure you write down that relationship. Let's talk a little bit about surface area. Again, surface area, if you increase the surface area, it also increases the rate of the reaction. Make sure you write down that relationship. In order to make this a little more visible, let's think about a stack of newspapers. If you have a stack of newspapers, only the top page is exposed to the air in the room. However, if you unfold all of the newspaper pages and spread them out all over the room, all of the pages are exposed to the air. This is kind of what it's like for increasing surface area with rate of reactions. The more surface area, the more reactants are exposed to other reactants, which increases the likelihood of a reaction. So make sure you understand that relationship between surface area and rate of reaction. The next one is stirring or agitation. Stirring or agitating reactants will increase the rate of reaction. So another increase. Make sure you write down that relationship. The best way to describe this is if you think about a washing machine. If you dump a bunch of clothes with water and soap in a bin and just leave it sitting there without doing anything, the clothes aren't going to get very clean because not all the clothes are exposed to the soap. However, what a washing machine does is it stirs the clothes around, mixes them together with the water and the soap, which increases the clothes exposure to the soap. The same thing happens with stirring and agitation during chemical reactions. The more that the reactants are stirred or agitated, the more likely they are to react. Okay, concentration. This was not one of your words that you had to look up at the beginning, so here's the definition of concentration. It's the number of particles in a given volume. So when you increase the concentration of the reactants, this increases the rate of the reaction. That's the relationship between concentration and rate of reaction. It stands to reason that if you add more reactants, they are more likely to react. If there's less reactants, they're less likely to find each other, collide, and react. The more reactants you add, the more concentrated it is, you increase the rate of reaction. Catalysts. This is number 5. This was the most important one. You should probably put a little star. Catalysts are very important in the study of chemistry and also in the study of biology. A catalyst is one of the definitions you should have looked up. I want you to double check it with the definition we have here. A catalyst is a substance that affects the rate of reaction, and just pay attention to these capitalized, without being used up in the reaction. That's very important. Catalysts affect the rate of reaction, but they're not used up, unlike reactants and products. So it is not a reactant and it is not a product. So not a reactant or a product. The way that catalyst works is it makes it easier for reactants to react. So it increases the rate of reaction. So it kind of does the job of bringing the reactants together. So it brings them together, but it doesn't participate in the reaction. Okay, it's kind of like a matchmaker. You know, you bring the people together, you don't really participate in their relationship, but you bring them together, you speed up their chemistry. So that's kind of what a catalyst is like. All right?